Good afternoon, everyone. I'm Zhipeng from Zhejiang University. Today, I will introduce our work where we develop a method to infer function intentions on memory management and detect conflicts of such intentions to identify memory bugs in Linux kernel. So first, let's briefly review the memory management or MM problems in C programs. So in C programs, ideally, every memory object allocated on the heap should be released exactly once. If they are not released, it leads to a memory leak problem. If they are released multiple times, it results in a double free problem. Additionally, if they are used after being released, use after free is triggered. Such memory management problem will affect the performance and the security of a program. And there are basically three main approaches to solve these problems. The first is data flow analysis, which suffers from path explosion when they are used in kernel analysis. The second is function pairing, and the third is similarity analysis. These two methods often rely on the correctness of code snipers, which is also hard to achieve. And here comes our insight. We found that the most memory release operation exists in error handling paths, where most memory bugs also occurs. Besides, the causes of these bugs can be concluded as unclarity of ownership and the lifecycle management of memory object. So we introduce the concept of intention, which refers to how a function intends to manage a memory object, both of itself and of its callee. In this way, inconsistent intentions between a caller and a callee leads to problematic memory management. And there are two types of memory management methods that is widely used in Linux kernel. The first one is called callee-based management. It is the most common strategy, and it simply asks a function to release the memory object allocated by itself on its failure. And their caller don't need to take any further actions. And the second strategy is caller-based management, where the release operation is left to the caller. Here we can see the caller calls to a free function to revert the status changes, while the callee did nothing. This strategy is also popular in Linux kernel. And due to the different strategies, there would be conflicts when there are intention inconsistencies. For example, if a callee function adopts a callee-based management and its caller also tries to release the resources, then usually memory corruption occurs. Conversely, if both the callee and the caller tend to leave the release duty to the other, and memory leak usually happens. These inconsistencies are often due to the complex error handling logic, imperfect code updating, and some implicit operation system mechanisms. So, in order to prevent MM issue from intention inconsistencies, we first need to infer MM intentions. We combine static analysis with a large language module to better understand both explicit and implicit mechanisms. And we also need to consider balance between precision and efficiency. Here we introduce demand-driven memory operation summation, which helps the overall analysis together with an object-based code slicing to exclude the irrelevant code and speed up our analysis. And here comes our system design. This is an overview. The name of our tool is IMI, stands for the inconsistent memory management intentions. We do some setup in our pre-processing, and the analysis part, the MM intention inference, and inconsistent analysis will be discussed in this section. So let's start with memory operation summation. The summary technique is actually practical here because the free function in Linux kernel follows a layered structure. For example, you can see the bottom layer could be k-free, and it's going up to debug areas free, and to debug info free, and to debug close. These functions act as just a wrapper of its underlying free operations. And these free wrappers usually contains relatively simple logics. And how we do the summary. The first step is to generate function-level summaries. Here we summarize the debug info free and debug close separately, and do not consider the core relationship between them. When we do need to summarize the memory operation of a function, we merge the summary of the function itself with those of its callees. By doing this, we transform the inter-procedure analysis of memory management into merging summary of different functions, allowing us to analyze each function only once. And then I'll introduce our code slicing. So remember, the goal of our code slicing is to find out memory object and error passes, and also to eliminate irrelevant code to speed up our analysis. For each memory object, we exclude code snipers before its allocation and after its nullification. And we also stop tracking into the caller if the memory object is not passed to it. And finally, it comes to our intention inference. For each memory object, we infer its management method from both its host function, namely callee, and its caller function. So first, let's see the callee inference. Callee inference determines whether a function releases a memory object in all its error handling passes. If it does, the object is in a callee-based management. If it doesn't, it's in caller-based. Otherwise, if the release is inconsistent, it is considered as an undetermined management. And an undetermined management is a potential bug, and we stop further analysis of its caller. Besides the callee inference, we also have caller inference. To those memory objects that is propagated to some caller function, we will infer their caller's intention to this memory object. So if the object is released upon the failure of the host function, it's caller-based management. If the object is released in the subsequent error passes, then it's callee-based. If the caller function simply returns the error code of the host function, we will track into the caller's caller. So we also utilize a large language model to assist with the implicit memory management mechanism, such as reference counting and indirect release core. And here is our prompt message. It basically consists of two parts. In the first part, we tell the large language model what is error passes. And the second part, we ask it to focus on specific mechanisms and determine if a memory object is freed in all error passes of a function. So then is a case study here. We want to show you how IMI works by this case. We can see that qdef LRG buff is allocated in the upper function. I think it's line 4, line 5, yeah. And, but it's not released on its error handling passes, indicating that the host function intends to caller-based management. Yes, it tends to leave the release duty to the caller. However, the caller frees the object in the subsequent error handling passes, and so it tends to callee-based callee-based memory management. And these inconsistent intentions eventually cause a mem leak issue. And then is our evaluation part. We use Clang 15 with kernel version 5.18, and the large language model we chose is GPT-4, and we only consider the response of large language model valid when at least 3 out of 4 responses conclude the same. And we find a total of 80 bugs, and 72 of them has been confirmed or fixed. And also, we can see here, the time cost of IMI is extremely low, that the static analysis over all the kernel code costs only 9.5 minutes. And here we can see that compared to existing tools, IMI effectively balance performance, precision, and the ability to uncover bugs. And with the help of large language model, specifically GPT-4, we reduce 32 false positives. Although it occasionally makes some mistakes, but only 3 true positives are misjudged. So here we can see GPT-4 has successfully identified the reference counting mechanisms and the indirect release core in kernel code. These identifications are still challenging for pure static analysis. However, as you may know, large language model sometimes suffers from illusion problems. For instance, here we can see that GPT-4 mistakenly inferred that QEDF free global queues will free QEDF global queues. It's very intuitive, but it's not a fact. The free function does not actually release the QEDF global queues. Actually, static analysis should be better on this problem. And in conclusion, we have our insight of why memory bugs occurs. And it is because the inconsistent memory management intentions. And second, we present IMI. It combines static analysis and large language model to detect such inconsistencies. And also, we use specific technique to reduce time consumption. And finally, we evaluate IMI on Linux kernel and identify 80 memory bugs effectively. So thank you for listening. If you have any questions, feel free to ask.